because of the low turnout, I kind of feel like we should have a quiz. So if everyone could take out a piece of paper, and here, let me write the quiz question, and of course turn off the video. Worst thing I've ever done. Okay, so sorry if you didn't make it to class today, so that's the quiz. So let's move on and just review. And that's why you're supposed to come to class. It's to motivate you to show up. That's why we do these. All right, class business aside, let's go over. So I was a little bit late posting the video. I did get very explicit in terms of how you're going to do electrochem questions. I did one example, I guess 2 examples, last Friday. I was a little slow to post the video. It's up now. But just to recap how that works and to be very explicit on like test taking strategies, remember that the way that this works is I'm going to give a reaction, 2 reactions, actually maybe 3, but let's not complicate it right now. We're going to have 2 reduction potentials, and so we call these half cells, half reactions. They're reduction reactions. They're called half reactions because it's half of the reaction, right? And of course I give the EMF, which is in volts, and these will be some number. And the first thing to do is rewrite them to be positive. So here, let me write down the algorithm. Sorry if I can spell right. Rewrite as positive EMF. Okay, that means that if this one is negative, then flip it and make it positive. And you do that so that all the delta G's are negative. Right, you don't ever want to consider a positive delta G reaction as potentially happening. It could, if it's the loser, right? But anyway, you want to consider only reactions that happen. Okay, with that, you then determine the winner, which would have the most, so then we have the delta G, and these need to be negative. Right, so you've assured that. All right, you then determine the winner, and that will have the most negative delta G. Although I showed an example, see now this is where I got confused. I'm almost getting confused again right now. I can feel that happening. Okay, let's not complicate it for right now. Let's look at these 2 reactions. One of them is going to have to be the winner. One of them has to be the winner. It's going to have the most negative delta G. And then you make the loser has to conform. Now what that means is you've got to cancel out the electrons. Okay, now this, I do want you to remember this because it's just 3 points. This isn't a lot this isn't hard. Okay, now what this means practically, let's say that these were both positive reduction potentials. That means that they want to be reduced. But reality is one of them wants to be reduced more. And so once you figure out which one that is, the other one is going to have to conform. If they're both reduction potentials, they have electrons on both sides, so one of them has to be flipped. The loser would have to be flipped to conform to the winner. All right, if one was positive and one was negative, then you really shouldn't have to do anything. Right, you're going to flip one no matter what. And yeah, so in your rewrite, you've already changed which one's positive, which one's negative, so you wouldn't have anything to do if they were on opposite sides of the fence. If they're on the same side, you're going to figure out which is the winner, and the loser is going to have to be flipped. Anyway, something has to get flipped because they're both reduction potentials. It's just a matter of flipping. Do you have to flip one because it had a negative EMF, or do you have to flip one because it was the loser? One way or the other, you have to cancel out the electrons. That's the end goal, and that's part A. Now part B, okay, in our algorithm of what to do is you add the delta G's, because what I want you to remember is, I'll call this little number prime, okay? So you sum them, and then you convert to the voltage of the cell. Okay, so why I'm asking you to do this, I don't want to treat you like a bunch of trained monkeys. That's not the point. So I don't like teaching these algorithms, but it does have a point, which is for you to remember that these are Hess's law. type questions. They just have an unusual, these half reactions are the numbers in the table at the back of the book. These are the reference states, right? The voltage relative to a standard hydrogen electrode. So that you know that these voltages are really delta G's. You know that delta G's add by Hess's law. And then you just use the Nernst equation, which is in the cheat sheet. Again, that's one thing you guys had trouble with. There were equations you needed that were in the cheat sheet. I don't expect you to memorize hardly anything. You've got to trust me on that. I don't expect you to remember hardly anything, especially on equations that you just have to use. So you look at the Nernst equation in the back of the book and you convert it to voltage. Okay, full credit. Question?
For the reaction G, wasn't that reaction G over F? I mean, I know it's a constant.
Yeah. What you do, this is minus this number times the number of electrons.
Okay.
Right, and so remember when it comes to this algorithm, the fact that Faraday's a constant appears is just ignored.
Okay.
And if you forget to just put it down in any particular place, whether it's the Nernst equation or here, don't worry. I don't care, that's fine.
Okay, so like if you were to just throw it in there anyway, so then when you add it, you're able to just plug in that value over the number of electrons to convert to volts. So
Well, yeah, I mean, it appears in a couple of places, but because of the way we scale electrons in this part and then scale them back, it kind of gets wiped out.
Okay.
Okay, so yeah, I don't, what I want to see is that you know this, that you know how to add them and convert it back. If there's some problems there, we're just talking like a point, right? Now, that means to me that you actually fundamentally understand this. Now remember, like Maxwell's equations, there's a cheat. Remember that you can just, having established that these have been written as positive, you figure out which one has to respond if they were both positive. If you need to have the loser respond, whatever, you just add the results. Okay, so algorithm, voltage, you get a number, then check. Check that once these have been written correctly by the winner and the loser conforming, if it needs to conform, that you just add these numbers and that they are the same as what you get here. That's how you check. Do not just do that, all right? Because, right, that means that you don't have any, that's you just memorizing something from freshman chemistry, which is next to pointless because a lot of what you learn in freshman chemistry is not true. Now, the reason though, I think it's kind of neat that that does work. For one, it guarantees you'll get the right answer. Number two, it's because that these EMFs, by the way, they're actually chemical potentials. Because they actually have, remember, they actually have the number of electrons, remember the Nernst equation or not, whatever. They have the number of electrons divided out. These are chemical potentials. And because of that, they're intensive, and that's why they don't scale with mass, and they can just be added together, right? So that's why that works the way it does. But ultimately, I do want you to know this, because that's a fundamental. Now, I also did an example. I already told you what I'm going to do on the test, is I'm going to have, to show me that you really get this, I'm going to have two possibilities for one of the reactions. And even if they have the same delta G, which is what I did on the example problem, and you saw me get really screwed up last Friday because I got confused myself. Reality is, if I give you two possible half reactions for one of the cells, so remember, I'm going to have one on the left that's absolute, and I'm going to have two possibilities on the right. And that will be because it's like water and oxygen, and I'll give you like two possible things that water and oxygen can do. When you do the analysis, it will still be the one with the most positive EMF that wins. Again, guaranteed that I want to see you do this analysis, but even if I gave you two possibilities for one of the cells, the one that has the most positive EMF here will generate the most positive EMF here and will be the thing that actually happens in this cell. The question?
Is there ever a case where there's a more negative change G but a more positive?
A more negative. Well, EMF and volt and G are the same thing. They're just related by that simple equation. I don't know what you mean. I mean, that's the same number, right?
Right, but if there was more electrons for one of the reactions.
In other words, I think what you're asking is, could you have an EMF here that, due to the number of electrons, is not the winner? No. All right, now, so remember on the example problem I did on Friday, I gave an example where the EMF of the 2-electron reaction was 1 and a 2 electron, sorry, if a 1 electron reaction was 2 and a 2 electron reaction was 1, giving you the same negative delta G. Right, and the way to answer that is, I did this analysis for both, that's what I'll have you do on the test, and the one with the most positive of the two, the one with the most positive EMF, still wins. And that was because of when you go through the algorithm, when you add the delta G's, the one with the most positive will always win. So that's why the cheat method is going to work no matter what. So again, on the exam, look at the extra hour. I give you two possibilities for one of the half cells. Go through the algorithm on both and show me that whichever one of these two has the most positive EMF still wins. And it will. And look at the example problem. So I'm not going to redo it because I already did it, all right? Okay, who's set? All right, okay, so anyway, so hopefully I've been very explicit. And I hope that these are just free points. That's what I mean them to be. And it's kind of questionable that I even go over this for a biochem class, but for one, I think it's free points personally. And number two, it's important because of alternative energy and all those blah, blah, blah. I try to scare the heck out of you out of, because this is the future of where humanity is going. So if anything, I like to use it just to, I spent nearly an hour telling you just about energy problems, which is your children's challenge, right? So, okay, anyway, and let me do a little bit of backing up here. Remember, big picture of this entire class, because we're basically only got about 20% left with all the holidays coming up and the test and all that jazz. We're basically almost done with this class. And so today we're going to do a really major hard left turn because, all right, so we started out with defining delta H's and G's and all that for gases. You saw that when you applied that towards actual chemical reactions, all those concepts just basically translate. You just have a Hess's law term, plus an entropy term that has all the things about mixing gases. So you see, I hope you see how I spent a lot of time talking about gases expanding and contracting because all those concepts were applicable to when an actual chemical reaction occurred. Now we did reaction quotients, you're doing it on your homework. The same concepts are alive when it comes to electrochem. That's what I'm going to query you on. Maybe that's a true and false question, as well as a battery question on the next test. I promise you you're going to have that. Now we're going to take a major turn. And what we're going to end up doing is I'm going to show you the concepts by which you can do these reactions. So now don't write this down. Don't write this down. I just want to remind you that at equilibrium, and this is per mole. All right, so remember that you were doing this for gases. You're doing this on your homework. But remember that we're doing this for a gas-phase reaction because what you have is K is the partial pressure of like B over partial pressure of A. So for A goes to B. All right, you end up with this relationship here, and that's for gas A turning into gas B, right? Products over reactants. What I want to get to is to show you how you're going to do this for biochemical reactions. And the answer, by the way, let me jump to the answer, is that partial pressures over partial pressures of something in solution doesn't make sense. What you actually are going to have are activities, right? Remember, in freshman in high school, you learned that these were concentrations. That cannot be correct because K cannot have units. It was an intentional lie meant to simplify things so that you could understand it. Reality is these are activities. Executive summary is I'm going to show you how to do activities, and once you understand activities and you want to do your biochemistry, you're still going to use this. These are going to be ratios of activities of products over reactants and not partial pressures, which how would you get the partial pressure for protein in solution, right? That's nonsense. Okay, so that's where we're going, and I'm actually going to start introducing the concept of activity in the same way I started to introduce how you think about reactions occurring, again, in the gas phase by first mixing. Right? Big picture again, as it pertains to the third test and the final, the thing about reacting gases, and I'm talking about about 2 weeks ago, was I introduced that to you. Remember, that was a whole 2-hour long lecture. I introduced it to you by talking about how gases would mix and how that lowers their delta G's, their G's per mole, That just happens, right? And that's an entropy thing because things like to mix that increases their entropy, that lowers their G. Again, that was a full 2 hours of lecture. And then I segued into reactions, but really they were the same thing, right? When the reaction occurs, you just get more mixing. The actual parts about bonds making and breaking, that's done in the Hess's law part. That's all taken care of. The rest of it is all due to just mixing, which just changes as you react. So I was really telling you about the same thing. Okay, so now as we go into actual some biochem, I don't know what the heck, liquid. Let's do the same thing, but we're going to talk about liquids mixing. All right, and this is how I'm going to introduce you to what activities are, and then knowing what activities are, you can figure out whether biochemical things react in solution by what I just showed. Okay, but we're going to start with mixtures. And what I'm going to do is I'm not going to talk about adding a protein to salt water like in your body. I'm going to actually stick with water and ethanol, just like I did gas when I introduced the idea of how you calculate how far a reaction occurs. I started with gases because, oh God, if I started with anything else, it would be like way too hard. When it comes to liquids and activity, I'm going to start with the simplest thing possible. I'm going to mix two liquids together. Actually, I'll start with mixing water into water. And to understand this, what we got to start out with is we got to start defining all the thermochemical H's and U's and G's and all that. We're going to start with volume. And I'm going to introduce the concept of a partial volume. It has a calculus definition, which will be on the cheat sheet. Now I gotta keep track that I've got an A and a B. And as I stated before, right when we segued into, when we got into delta G and delta A, once we started Legendre transforming away the entropy dependence and started thinking about temperature dependent things, I said from now on we're going to be at constant T and P land, because why not? Okay, so this is how the volume of a solution changes as I pour something in. Again, we are going to stick with constant T and P land from now on, because why wouldn't we? Anything else would just confuse us. Here's another little bit of notation. I'm going to add that you don't need to worry about this. What this notation is meant for you to understand is that there's two things present. Oh, sorry, I screwed this up. It's, and A is not equal to M. No, it doesn't matter, does it? Okay, it doesn't really matter which one I put, sorry, but just do OCD. This little notation is just meant to get it through to you that I'm talking about a mixture. It just implies that, hey, I'm talking about A, just so you know, A is not equal to B. It implies that B exists, it implies I'm talking about a liquid mixture. The reason not to worry about this is that any question I ask you with this in it is automatically going to be about a liquid mixture. So I don't need this symbology to remind you. This is just symbology that we use for liquid mixtures. So don't worry about it. It means nothing. Okay. And we call this little thing B with a hat. Because why not? It's a little bit easier. Okay, here's an example. And again, I'm going to start with the simplest thing possible, which is pouring water into water. So if I add 1 mole of water to water, what is the volume in, sorry, let me write this out in English. All right, what is the volume increase? Okay, this is a high school level question. I add 1 mole of water to a liter of water. How many liters, milliliters? How many milliliters do I have? How many milliliters has it increased? 1 mole of water is how many grams? 18. Therefore, the volume has increased 18 milliliters. Okay. That's something I probably would go over with a 5th grader. This is college level. If I add 1 mole H2O to excess ethanol, and I'll use water ethanol. I want to know the volume increase is what? Right, that's the question. Okay, now, if I was doing this with a 5th grader, They got this part right. Now, what do you think they would say here? 18? Now, what do you think? You think it's 18? Who thinks it's 18? The exact same number. Like, nothing is different, whether it goes into water or ethanol. It'll be exactly the same. What does your gut say?
No.
Your gut says no, right? Good. It should not be the same. Why would it? Of course not. Things are not that. Here's how you should know that. Nothing could be that easy, right? And you know that. So therefore, if I ask this on the test, I'm not, because it's that simple. You should know that no, it will not be 18. Because you're basically trying to put a round peg in a hole. So here, let me use the right units. 18 mils per mole, 14 mils per mole. Of course not. It is because water is a small little sucker and ethanol is kind of big. Water hydrogen bonds in a really tight little ball. Ethanol doesn't. Ethanol can't hydrogen bond as well as water because it's only got one OH. Water has two. Water can double hydrogen bond. Ethanol can only hydrogen bond once. And that means that water has this way of kind of sneaking in between all the ethanols, all the space that's already kind of there naturally. So, of course, that doesn't mean that the delta V is 0, but it's not nearly as big as it erstwhile would be. And so that just kind of makes sense to me. All right, now, I've given you this information, so now let's do this. Now I'm talking about water-ethanol mixtures, and I want to know what the volume of a solution is composed of water and ethanol. And let's use calculus language to do that. And the point of this is a lesson in converting equations to actions, which is something I told you. Any equation that is based on physical principles can be converted into something that can be described as an action. So what I interpret this is I am going to have a bucket and I have two solutions. One's going to make it fun. We're going to make it water and ethanol, and I'm going to pour them in. And this tells me how much volume increases based on water, and this will tell me how much volume increases based on ethanol. I will do 1 mole of water, 1 mole of ethanol. Now, one thing, just so you have this kind of right in your head, it doesn't matter. Remember that the ethanol is actually really big. This is a big container of water. It's 18 mils. That's pretty small. 1 mole of ethanol is actually a lot. That's 56 mils. 1 mole of water is 18. Don't worry about that. I just want to remind you that that's how it works. Okay, now, the problem is, what are these numbers? Let me give you a graph. So, and get used to this. I'm going to be doing a lot of drawing two graphs on top of one. I'm going to make a graph that is a function of mole fraction of ethanol. It will go from 0 to 1. So this is pure water. This is pure ethanol. And what I'm going to do is I'm going to have the partial volume of water, and that would be in mils per mole. Sorry, I'm writing way too small. This will be the mole fraction, the partial volume of ethanol. It will also be in mils per mole. Now, of course, pure water needs to be at 18. Sorry, this is hard to see. This is 18. And again, sorry to do it this way, but I'm going to draw data, 14. And the way it looks is like this. This is how that looks. So it goes from 18 to 14. Okay, and when I draw two graphs, I'll make sure you know what line corresponds to what. Now let me do ethanol. Ethanol will start at 58. So so 1 mole of ethanol has X number of grams. Then you look at the density off some website, and you'll find that pure ethanol adds 18 mils per mole. Anyway, and then the bottom number is 52. Okay, and it has a structure kind of like this. Try to get this right. Notice that they're kind of mirror image-ish, kind of. And I need to make sure that, actually here, I didn't quite do this just right. Let me, I'm being OCD, sorry. There, that's a little bit better. There we go. I wanted this to be about in the middle. About 54. I didn't do a very good job drawing this, but whatever. Notice that they're kind of mirror images, and I'm going to talk a little bit more about that in a second. Okay. All right, now again, equations have actions, and here's the data. All I'm trying to do is mix water and ethanol, because as much as it's James Bond on pouring a drink, I can actually imagine industry probably uses such mixtures as coolants, maybe as alternative energy. This is the kind of thing people need to know. I'm sure there are industries, not just the liquor industry, although I'm sure they need to know this, about how these partial volumes mix so that you know what the heck your chemicals are doing. And again, this is the equation for total volume. All right, now, I want to know the total volume. You got to think about this. It's kind of it's like a little quiz, like a little clever trick. Now let's do ethanol first. What I'll do is I get my container and I have 1 mole of ethanol, that's 58 mils. I pour it in, now I have 58 mils total. Okay, so this part's done. Now let's do this part. I'm starting to add the water, and that first, say, 10% doesn't add 18 mils like you kind of think, like the 5th grader thinks it would. Instead, it adds 14 mils, right? Okay, so that's the first 10%. The next 10% actually creates a little bit more volume. Looks like it's about 15 mils per mole as I add that extra 10%. Now I'm going to add another 10%, and it looks like it's adding 16 mils. You see, this number is changing. It's a function of composition. As this goes up, the composition changes from pure ethanol to 50-50, and that means that that number is changing according to the data in this graph. All right, now I hope that's kind of obvious, and this is why we have calculus to solve this kind of jazz. Maybe I have to come up with some equation, maybe it's like a sine function or some Taylor series to get this data as a function of mole fraction in here, and then I can calculate it. But here's my point. This is awfully complicated. This is how it works, but this is awfully complicated. What I really want to do is work with one number and just solve it just by partial volume delta and 1 mole, partial volume 1 mole, right? Now how can I do that? Okay, again, now let's turn this equation into an action. This is why I want to go over this. It's kind of stupid, I know, but I want to make sure that here and everywhere else, these equations have meaning, more than just an equation. I have 1 mole ethanol, 1 mole water. What I want to do is pour them into a container to get this, such that I don't need this data. Maybe I just need this data point to figure out what the total volume is. How do I do it? Now, before I poured in the ethanol, then I poured in the water, and I screwed myself because I needed to use all this data. I needed to use calculus to solve this because this guy's continuously changing. Or what could I have done differently? To just have used one number, say at the halfway point, right? I could have read this off the graph. How could I have done that? Now again, the first possibility was pouring in the ethanol and then the water. Instead, pour them in at the same time, right? That way the first drops that hit the container were instantly at the 50-50 per mole mark. And as I added more water and ethanol at the same time, at the same rate, these numbers didn't change because the composition never changed. It was always 50-50, right? So anyway, there you go. That's all I have. So let's just drop all of it now, just kidding. So let's go further with this. And I do want to show off one neat thing about this is why they're kind of mirror images. Because when I was taking this class, I find when I see data on two related species, whether partial volumes or just about anything, I often see mirror image-like behavior. And it turns out there's a reason for this. And this might be the subject of an extra credit question, like the hard one at the end. Let me show you why these look this way and why you see relationships between things that are, I mean, clearly water and ethanol are related because I'm mixing the two. All right, and they are almost mirror images, but not quite. That seems like it should be, but notice that it's just not quite the same. And so I'm going to explain why that is. And it's kind of this neat little factoid that I'm not going to emphasize in a test or a final, except perhaps in the form of an extra credit. And this is called a Gibbs-Duhem equation. And what I do like about this is that it really does show me that you get how these equations have and that you can hack the calculus. And this is kind of childish. I'm not going to do something insane like E equals MC squared. I just want to point out, here's equation 1, that the change in volume of this is the unintegrated form of that, right? So what I've shown up there is the integration of what I'm doing right now. Partial volume of A, partial volume of B. Okay, again, this is how much this solution, how much volume is being added as I pour in the water and ethanol. Up there, that's just the final result. Okay, now what I'm going to do is, notice that equation up there. Watch this. Now I'm going to integrate the whole thing. I'm going to get V is, I've just integrated this. Now what I'm doing up here is I'm assuming that the lower limit in the integrals is 0. Actually, yeah, exactly as I've done, because that makes sense, right? Oops. Okay, so this is number of moles of B because the initial was 0 and the final is number of moles of B. Okay. Okay, now hold on a second. Now so hopefully this is, again, high school level. Notice, though, let's take the derivative of this. Let's take the derivative of this. We're going to do it the way I have been showing you to do this, which is correct. Which is that I've got partial volume of A, change in moles of A. I got the partial volume of B, change in moles of B, right? But I'm not done. Product rule. N sub A, change in partial volume of A, moles of B, change in partial volume of B. Now remember, these do change with composition. The data is right up there. It is legit to think about how partial volumes change because they do change. It's right up there. These are not static numbers. This isn't what's the change in V at constant partial volume of A. This isn't the change in V at constant volume of B. I've just done product rule. I've just taken this term and I changed the partial volume. I left this one constant, then I let this one change and I held that one constant, just like I've been showing you the whole time. Now the only issue is, this part is here, and this part isn't. And you know that this is right. Of course you know this is right. I'm just talking about pouring 2 liquids in a bucket. Like you haven't ever filled a liquid. Anyway. Good. Anyway. Totally gonna cut that. This is 5th grader knowledge. But the calculus isn't wrong. And it's not. The calculus is not wrong. So what in the heck is happening here? Right? This term has to be here. This is just normal calculus. Normal calculus hasn't just failed because I'm talking about adding liquid to a bucket. Resolve? How can you resolve this? Yeah, it's, I don't know if you're going to get it. What it is 0. It turns out to be 0. Don't write that down that way. That's confusing. It makes the whole thing look 0. Therefore, N sub A, change in the partial volume of A, plus N sub B, change in the partial volume of B, is equal to 0. And it's called a Gibbs-Duhem equation. It basically means that these two things, they kind of feel each other out, such that when ethanol sees water being poured into it, it changes its partial volume to basically negate what the water is doing. That will be more clear. Let me write it out this way. The change in partial volume of A is equal to this ratio of mole fractions. Okay, so again, what ethanol does as it sees water getting poured into it, it's going to change its own partial volume basically to negate, to be opposite of what the other one's doing, weighted down by the relative number of moles. Okay, so what that means is that, for one, this is why one's the mirror image of the other. That minus sign is doing it, right there. Again, remember, this is all very simple mathematical, right? All right, a little bit of calculus, and that is new to you, I know that, but whatever, it's just the product rule. A little algebra gives us a minus sign, and nature gives us a minus sign too. That's the reflection. Notice that, and I did draw this relatively accurate, notice that it's not a perfect reflection. It's actually this right here. This is doing that. Because what's happening is, and I don't want to get into more of this, but it's an algebraic nightmare. What you have to do is to turn this NA over NB over NA, you have to turn that into mole fraction, right? They're obviously related, but they're obviously not the same thing. So when you do the algebra to turn this into this, it gets really kind of a lot more complicated, but it gives you the little bit of structure. In other words, all right, mirror images minus sign, the fact they're not perfect is actually this ratio of moles doing it. And yeah, and it works really freaking well. So anyway, so that's really all I wanted to cover. There's actually a lot of things that do this. You can actually explain a ton of behavior with these Gibbs-Duhem relationships, and I may put one as an extra credit question on the next test. In fact, I'm just going to go ahead and tell you I'm going to do it. I won't do this. I'll tell you what, an extra hour Friday, I'll do one and I'll make it clear what I'm going to do. But anyway, it's just kind of neat. I always got fascinated. The first time I covered this class, I wasn't aware of this. It's in your book, by the way, but the book I was using didn't have this. And I was just really curious why they were almost perfect images of each other, but not quite. And again, in your book, it actually does cover these Gibbs-Duhem equations, so that's why. Anyway, I don't want to say anything more about that. Actually, what I want to do is, all right, thermodynamics. Thermodynamics of mixing. Now that we've got volumes, let me get to delta G's and delta S's, because it's kind of, why do things mix? I'm going to do a lot of things that are similar for gases. Why do gases mix? Gases always mix because their entropy increases, and you don't really have to worry about, so that's delta S. What about delta H? Because delta G is delta H minus T delta S. Delta S is clearly going to go up. Delta H really shouldn't change at all because gases largely don't interact. That's not going to be so true with liquids, so I think you can kind of see where I'm going with this. What I want to do is define excess. These are called excess functions. Sorry, my handwriting is not great today. Excess functions, these are how thermodynamic properties change when things mix. They are going to be on the cheat sheet. They're very simple. And as usual, I need to put the process, change in what process of what. That's our symbology. This will be the volume that we were calculating before, minus V star. Now what this is, volume, it's the sum of the volume of pure liquids. Okay, so in our example of 1 mole of water and 1 mole of ethanol, we know by heart that the 1 mole of water is 18 mils, and remember density, molecular weight, blah, blah, blah. The volume of 1 mole of ethanol is 56. So our 58. So this would be 58 plus 16. And then this is the result of our measurement or our calculation, whichever one, they would be the same number. Okay, and the way that I will express this mathematically is this. I'm going to have a certain number of moles, and I'm going to have the partial volume. Now, this is a little funky right here. This is just the volume per mole. All right, this is 18 mils per mole for water. This is 58 mils per mole of ethanol. There you go. Right, it's just a property you look up in a Merck-Index or a CRC, right? It'll be given to you on the test if you need it. This comes from those data tables up there. This is, if this was, let's say that this was water going to basically pure ethanol. So that's on the far right of the graph. Ethanol, both these numbers would still be 58. right? Because the ethanol is essentially pure. But when it comes to water, this would be 18 and this would be 14, right? So wait, yeah, this is 18 because that's pure water. But if water's going into pure ethanol, I'm looking up there, it's 14. Okay, so anyway, right? Really simple stuff. And there isn't much to think about this. This is how I use partial volume with mixing. There is unfortunately a partial volume for just about everything. And instead of A's and B's, I'll just use a generic letter I. Don't even try to worry or memorize about that. It doesn't mean anything. I'm going to use the same symbology. We're still at constant temperature and pressure. And I'm just going to use a little bit of a different symbology. I'm going to use I's and J's instead of A's and B's. It's just a little bit more generic. It's the same idea. Again, the enthalpy of something from the table in the back of the book is for a pure substance, and let's do liquids, because that's what I'm talking about. I know what the enthalpy is of a pure substance from the table in the back of the book, but it's going to change because you're mixing. Remember, this is the thing that says that you're mixing. Don't worry about that. Obviously, the question is going to ask you about something mixing. It's obviously a mixing question. Okay, again, enthalpies of things change from the number in the back of the book when you mix them together. Now that's relatively brainless. Maybe that Gibbs-Duhem thing, that's kind of cool, I think. That's college level. This is kind of brainless. Likewise, I have entropy of mixing, which is the same thing. I wouldn't write it down. I just have to, I am kind of required, I'm obliged to put all this jazz. And there's obviously a Gibbs energy of mixing, which needs to be, hopefully is negative if things mix. Again, if the number in the table of the back of the book is changing, and I've got to put all this T and P stuff, this Ni not equal to Nj implies that there is a J present, meaning that this is a liquid mixture, yada, yada, yada. Now, if things mix, I need to analyze it with delta G, because again, I'm always going to be in a constant temperature and pressure world. But instead of, so let me write that down. Ultimately, because we're in a constant temperature and pressure world, where I'm heading with this is, does it mix, does it not? And next lecture, that will lead us into understanding what activity is, and that way you actually know how reactions in solution occur. But I didn't say that, so don't worry about that. Okay, given these partial quantities, then I can define the excess function. Sorry, I almost got the symbology wrong. Okay, the delta G of mixing will be the sum of things in their mixed state minus the pure state. And the same stupid little equation applies, where I get the partial minus the number in the table in the back of the book. Okay? This is all fine and good, and if things are going to mix, this is going to be negative. But I am not going to analyze anything this way. I am going to analyze it, but I'm going to analyze it this way. Because it's just easier, actually, and more informative. Hopefully this is kind of obvious. Okay, so, again, do things mix? I need a negative delta G. That's all fine and good, but I'm going to give, as we're going to analyze does it mix, I'm actually going to use this equation. Because, now this is relatively simple. We're going to describe this. Let's do delta H mix. Sorry, let me, okay, and delta mix H. And I'll stop here. Of course, this is going to be delta U mix minus P delta mix. And notice that the V delta P mix is not there because we're at constant pressure. Right? So again, it's clear, hopefully, from like test 1 material. Okay. Now what I'm going to do next time is I'm going to show you that ideally all liquids mix because nothing happens here, and so entropy makes things mix, just like gases. That's ideally. But you know that oil and water doesn't mix. And what I'm going to show you is that Well, this is always going to want to make things mix. This is going to fight you. So that's next time. That's again why oil and water doesn't mix. And then after that, we're going to figure out why things react with activity. Okay.